The Lewis structures of molecules is going to be a little bit more difficult than they were for ionic compounds. Remember, molecular compounds contain covalent bonds, and covalent bonds means that electrons are being shared. Also remember that molecular compounds are typically formed when we have a nonmetal bonded to a nonmetal. So that's how we can anticipate that we are dealing with a molecular compound. Remember how we treat the Lewis structures for ionic compounds and molecular compounds are different, so it's important to be able to identify which one you're dealing with. The Octet Rule is still very important for the structures of molecular compounds, and we've previously discussed this, that the individual atoms inside of a molecule wants to have 8 electrons around it. They want to gain an electron configuration similar to a noble gas. Most noble gases have filled S and filled P subshells. 2 plus 6 is equal to 8, and this gives a stabilizing effect in terms of having full subshells. Remember, the one important exception to this is hydrogen and helium. They only want 2 electrons, but just about everything else that we're going to be looking at, all the other atoms are going to want 8. And there are still more exceptions to this octet rule. But for right now, when we're drawing Lewis structures, any other atom other than hydrogen wants to have 8 valence electrons. There are certain exceptions to this, but for right now, that's really what we are looking for. With molecular compounds, we are going to also see lone pair electrons, and these were the electron pairs that we saw in certain Lewis symbols. An electron pair is not involved in bonding, so it's unpaired electrons that are going to be involved in bonding. When they're paired, they do not want to bond with other atoms, but we still need to identify and show these electrons, and we do it by putting them in pairs, and these are going to be called lone pair electrons. To draw the Lewis structure of a covalent compound, you still start with the Lewis symbol for each element. So you draw the elemental symbol and then put valence electrons around it. And here we are going to connect unpaired electrons to form bonds. And this is going to represent the sharing of electrons that we have with covalent bonds. And this is an important rule. Each unpaired electron inside of a Lewis symbol should form some kind of bond. And when you are done drawing the Lewis structure of a molecule, if you have any unpaired electrons remaining, you probably have done something wrong. So lone pair electrons are okay, but unpaired electrons means that you probably have made a mistake at some point. There's one way that we can double check our answer when we're done. And the idea is the electrons we get out in our structure must equal the number of electrons that we're putting in. So the number of electrons that we're putting in is equal to the number of valence electrons that we're putting in. So if you look at each individual atom, say how many valence electrons do they have, and add them up, and then divide by 2, that's how many electron pairs which we should see in our Lewis structure. And in this case, the electron pair is either going to be a set of lone pair electrons or it's going to be a bond. So we can check and make sure that we have the proper number of electron pairs inside of our proposed answer. So we start off by drawing the Lewis structure of Cl2. Once again, you want to start with the Lewis symbol. So we have chlorine here. We look at the periodic table, we find chlorine has 7 valence electrons, and we understand when we represent these 7 valence electrons, it is 3 pairs of lone pair electrons and an unpaired electron. And the idea is each one of these chlorines is 1 electron away from having an octet. And how these chlorines are going to gain an octet is by sharing an electron. So literally what you do is connect these 2 unpaired electrons. You connect the dots, and then this is going to form a bond. These 2 electrons go into this bond, and we represent those 2 electrons by a bar. In doing this, each chlorine now has 8 electrons. So if we count the electrons around each chlorine, we have 2, 4, 6, and now this bond, 8. 2, 4, 6, 8. So by sharing an electron, both chlorines now have 8 electrons and have gained the stability of our noble gas configuration. We can also check our answer here. We know that we put in 14 valence electrons, so we have 2 chlorines. Each chlorine has 7 valence electrons. 14 valence electrons divided by 2 means that we should have 7 electron pairs inside of our structure. And each electron pair is either a set of lone pair electrons or a bond. So when we count it, 1, 2, 3, 4, 5, 6, 7, we can see that we have at least the proper number of electrons inside of our answer. Continuing on, we look at the Lewis structure of water, H2O. Once again, we go and look up and create the Lewis symbol for each one of the atoms inside of our molecule. Hydrogen has 1 valence electron, oxygen has 6 valence electrons, and you begin to see the idea here that oxygen has 2 unpaired electrons, so it is probably going to end up forming 2 bonds, and that's quite true. Each unpaired electron forms a bond. Overall, still what you do is connect unpaired electrons. So one unpaired electron from oxygen connects to an unpaired electron on hydrogen to create a bond. And the same thing happens on the other side. And when we look at it, the oxygen, when we're done, has 2 sets of lone pair electrons and 2 bonds. And in doing this, our oxygen now has 8 electrons around it. So when we count it, 2, 4, 6, 8, the oxygen has the octet that we are looking for. We can also count the number of electron pairs that we should have inside of our answer here. Each hydrogen had 1 valence electron, so we had 2 of those. Our oxygen had 6. We divide by 2, and that tells us that there should be 4 electron pairs inside of our answer. So we have 1, 2, 3, 4. And so our answer has the proper number of electron pairs. So thus far we've looked at what's called single bonds, a single connection between 2 atoms, and 1 electron from each atom being shared. We can have more than 1 shared electron between atoms, and that's going to create what's called a multiple bond. So the next one we're going to look at is called a double bond, where 2 shared pairs of electrons are going on between 2 atoms inside of our molecule. So we're going to look at CO2, and this contains 2 double bonds. So still, I start off by drawing the Lewis symbol for each atom inside of my molecule. Each oxygen has 6 valence electrons, and when we look, each oxygen has 2 unpaired electrons. Carbon has 4 valence electrons, and remember the way that we've drawn it, with 4 valence electrons, each electron is unpaired. So that means carbon wants to form 4 bonds. So carbon wants to form 4 bonds, each oxygen wants to form 2 bonds, and in the next step what we end up doing is connecting unpaired electrons. 2 unpaired electrons from carbon are going to connect with 2 unpaired electrons from this oxygen. 2 unpaired electrons from carbon are going to connect with 2 unpaired electrons from this oxygen. And with 2 unpaired electrons connecting, what we end up forming is a double bond. So between carbon and oxygen, there's actually 2 pairs of electrons being shared between them. And this is going to change the properties of the bond. So single bonds and double bonds have different properties that we will talk about later. And one thing to note at this point is Lewis structures do not imply geometry. So it really doesn't matter how you draw these bonds and electrons. There's no specific geometry that you can gain. But what is important to have is the correct number of bonds and lone pair electrons inside of our molecule. At this point, don't worry about trying to put things in a proper geometry. Just make sure that they are clearly attached to a specific atom. So in this structure for CO2, once again, we can check our answer. We have 2 oxygens with 6 valence electrons and a carbon with 4 valence electrons. We divide by 2, we get that our answer should have 8 electron pairs. So if we look, 1, 2, 3, 4, 5, 6, 7, 8. So it has the correct number of electron pairs. And then also notice all of the atoms inside of our molecule have 8 electrons around them. Specifically the carbon now, we count each one of these bonds as 2. So there's 2, 4, 6, 8 electrons around our central carbon here, fulfilling its octet. Lastly, we can have up to 3 shared pairs of electrons, and this is going to form a triple bond, which is represented by 3 lines. So remember, each line represents 2 electrons being shared. The classic example is N2, which has one triple bond. So we can take a look at nitrogen. First thing we do is draw out the Lewis symbol for each atom inside of our molecule. So each nitrogen has 5 valence electrons. And that tells us here that each individual nitrogen has 3 unpaired electrons and 1 set of lone pair electrons. This nitrogen wants to have 3 bonds, and this nitrogen wants to have 3 bonds, and we know this because they have 3 unpaired electrons. The next step, we connect each unpaired electron, and those are going to turn into an individual bond here. So we can see that nitrogen and the other nitrogen are connected by 3 sets of shared electrons to form a triple bond. And in doing this, this allows each one of our nitrogens to have 8 electrons around it. So if we count 2, 4, 6, 8, we can see that both of our nitrogens have the electron configuration similar to a noble gas.